Gabrielle Cordero, and I'm a 10th grader at Washington Liberty. My project is on the effect of detergent products containing sodium percarbonate on luminol efficacy. So I've been interested in forensic sciences from numerous shows and novels, and I wanted to use this interest to be the inspiration for my project. I was always impressed by how forensic scientists could find crucial evidence using technology such as luminol tests. For those who don't know, luminol is used by the police to detect blood at crime scenes, including on garments. However, recent studies have suggested that new laundry detergents contain an ingredient known as active oxygen or sodium percarbonate that is hinted to be possible to remove blood stains from clothes that would otherwise be detected by luminol. So this experiment will enable crime investigators to further our understanding of crime reconstruction by considering the possible flaws behind luminol tests. So, as I mentioned before, luminol is a common method to detect blood, and it does this using a process known as chemoluminescence. How it works is that when it detects blood, the luminol solution reacts with an oxidizing agent and the hemoglobin's iron found in red blood cells, and it goes into an excited state, and when it comes back down to ground state, that's when it emits the light, the blue light that you see when you have a positive test. Luminol can also detect metals such as iron and copper, which affects its accuracy and reliability. But on a different note, sodium percarbonate is a chemical compound that has replaced chlorine in our laundry detergents in recent years, mainly because of health safety concerns. But it's also significantly stronger. So when dissolved in water, sodium percarbonate releases oxygen, which frees up the hydrogen peroxide and sodium carbonate, both of which are very strong bleach agents, which could negatively impact luminol detection if it's strong enough to remove microscopic traces of blood. So, an obvious setback in my experiment is that blood of any kind can't be used for science projects, so I had to look for an alternative, and what I found was myoglobin was very similar. It also creates a positive luminol test, and chemically speaking, they are both cytoplasmic proteins that bind oxygen on a heme group. Hemoglobin is an oxygen carrier found in red blood cells, but myoglobin stores oxygen in muscle tissues. But after doing some research, I found that myoglobin has a much higher limit of detection with 40,000 femtomoles, while hemoglobin only has 0.1 femtomoles. So theoretically, hemoglobin is much easier to be precisely measured than myoglobin by luminol. Just like more like general properties, blood and myoglobin are cleaned using very similar cleaning techniques, which has me think that they also have very similar staining properties. But the only thing I could think of that would clearly set them apart is that they have different consistencies. So hemoglobin's more likely to clot than myoglobin, which could affect my experiment. But other than that, they're very similar. My research question for my experiment asked what is the effect of detergent products containing sodium percarbonate on the efficacy of luminol, and my hypothesis was that if clothing fabric was soaked in myoglobin and washed in laundry detergent containing sodium percarbonate, then there will be a negative luminol test because sodium percarbonate is a bleaching agent and oxidizing agent that's capable of removing microscopic traces of iron that would normally be detected otherwise. So the dependent variable for my experiment was the presence of active oxygen in detergent. The control group would be the group with myoglobin-soaked fabric washed with a natural detergent lacking active oxygen, while the experimental group would contain active oxygen in its detergent. I decided on measuring the percentage of positives out of 20 trials, and some of my constants on my experiment were the washer and drying settings for each group and the fabric type. So how I did it was I purchased a dry 15-gram powder luminol reagent bottle container and filled it with 250 milliliters of distilled water to activate the luminol solution. Strips of 100% cotton fabric were soaked in myoglobin that came from packaged raw beef, as seen in the photo to the left, and tested using a luminol solution to ensure there was a positive test before being washed. The control group was also went through the same process and was washed using a natural detergent that didn't contain active oxygen, the one on the left in the photo on the right. And the experimental group was washed with Tide, a chemical detergent. The suggested servings for each detergent was applied to the load depending on the different detergents. And after being washed and dried, another luminol test was performed, and the percentage of positive luminol test data and as well as qualitative observations were collected. What I found was that my data was insignificant. 100% of the fabric strips tested positive out of 20 trials for the control group and the experimental group. There was also no clear qualitative differences, like the luminol color intensity remained the same. And no T-square was performed because of the lack of diversity in my data, and no T-test was necessary to conclude that the null hypothesis couldn't be rejected. So, sodium percarbonate did not produce a negative test and therefore does not support my hypothesis. This surprised me, and I was puzzled as to why the experiment contradicted other experiments that had research that had contradicting conclusions. So, in an attempt to understand to see if there was any experimental errors in my experiment, I tested some of the constants, including the presence of myoglobin in each trial, the effect of the chemical detergents, and the effect of a luminol test prior to the wash cycle. I added my results from testing prior to washing the clothing fabrics from the previous experiment to this table because it demonstrates that there was a positive test to begin with before being washed. By testing the active oxygen's effect on the luminol test without myoglobin being put on the strips, I wanted to ensure that it was the myoglobin causing the positive test in the experiment and not created by the detergent or any other substances. And I also tested how performing a luminol test on the fabric before washing it might have impacted the second luminol test. The reason for less trials at the table was because I learned from my original experiment that there isn't much diversity in the percentage of positives, so I didn't think it was necessary. So here are my results. When the strips were washed with the active oxygen detergent and no myoglobin, there were no positive luminol tests, which meant that the positives from the original experiment must have come from the myoglobin, which ensures that other ingredients found in the detergent didn't interfere with my results. And in the original experiment, it was also confirmed that each strip actually had myoglobin to begin with, because of the 100% of positives. And then when there was only one luminol test performed per trial after being washed, I gathered in 100% positive. So that indicates that the first luminol test in the original experiment lost its effect by the time the second luminol test was administered. In conclusion, none of my tested experimental errors really took away from the authenticity of my experiment results, and the null hypothesis was still accepted. Although this came to me as a surprise, the null hypothesis is good news for criminal investigations, because it means that scientists can depend on luminol test without having to question its legitimacy. But again, there are scientific studies that have suggested otherwise, and after further investigating those sources, I learned that one study used pure sodium percarbonate, which is a possible explanation for the contradictory result. I think the most important thing I learned from the whole science fair process was learning how to problem solve within the scientific process, because at first I was disappointed in the null hypothesis because I assumed that it meant that I had failed my experiment and I was going to give up. But after talking to my teacher, I learned that you can still do a lot more with a null hypothesis and it doesn't take away from my experiment. I also learned that the scientific process doesn't end at the conclusion. I continue to learn more about the possibilities of what I could have done differently and other possible explanations to my result. I think it would be beneficial to test using actual hemoglobin on different clothing fabrics, such as latex or maybe silk, as well as testing different concentrations of sodium percarbonate and its effect. Here's some of the important resources I used throughout my experiment. Most notably, the first two are the studies that I refer to in my presentation. I only had the abstract, but even then it gave me insights on luminol's function and the skeleton for my project. And then the last two are both either for real-world context or like scientific explanations.